This is original. This is pixelated. Again, this is original. And this is pixelated. Great. Hello, I'm Jack. Today, let's talk about how to pixelate images in p5.js. Let's dive right in. So before we pixelate image, let's see how we can load image and display it on this canvas. And I already named my sketch loading image, and let's see how we actually do it. So in the text editor section of the p5 web editor, you'll notice there's a button that's pointing to the right side, an arrow. If we click on that, this is where you get to see all the files that's in our sketch. And what we've really been mostly editing is a sketch.js file. But now we want to bring an image file in our sketch. What we do is click on this arrow, the plus button. If we click that, we can choose upload file and click this again. Then you can identify the image you want to load. In this case, I want to load this image called mycodingshow.png. I'm going to click on that and then click open. So now this image has been uploaded. It's uploaded to the sketch, to the server of the p5 web editor. And we can verify that by clicking on the .png file and see our image. And now let's click the .js file and I'm going to click this arrow to hide it for now. So now we have the file. How do we load it? In order to load the image, there are a couple of steps. One is let's give the image a name, or let's create a variable to hold that image. And this variable, we can give it any name. In this case, I'm going to call it img. And that is because image is already a reserved name for a function, which is what we use to display image. So I'm going to avoid that and call it img. And then we need to start using additional functions other than setup and draw. So let's follow the same format as setup and draw and write a function called preload, because for image files like image, we need to preload that before we start a sketch. This kind of file takes a little bit of time to load depending on how fast your internet is. And inside of preload, since we already created the img variable, what I'm going to do is img equals to load image. And again, just follow the same format as any other function, load image, parentheses, and semicolon. So within the parentheses is where we provide the path to that image. In our case, it's just the name of the file. So mycodingshow.png. And I'm always in the habit of running the code all the time, even though I'm not expecting anything. And that is because when I run the code, if there's no error in the console, it's a good indication that I'm probably not making any major mistakes. So it's always good to keep running the code from time to time. And in fact, if you can, whenever you make some changes, try to run the code just so you see there's no errors. That's always a good reassurance. So now we've load this image. That means before the setup happens, the p5 library is going to help us load that image into this variable. And then how do we draw that? So let's put that inside of the draw function. We use the image function to draw image. And there are a couple of parameters we need to provide. The first one is the actual image variable, and then followed by the position of that image, the x and y coordinate, and then followed by the width and height, similar to how a rectangle would normally work. So for now, let's say, what if I want to draw at 100 and 100? There you go. You see how it's like was slow a little bit at the beginning. That's when the image was loading. And now once it's loaded, it's drawing the image at the top left corner. As you can probably imagine, if you want to draw the image on the entire to fill the entire canvas, you can either put 400, 400, or I can use those two special variables, width and height, because that's dynamically changing depending on what the actual width and height of the canvas is. So if I'm make the canvas a little bit wider, the image will also follow that format and get stretched a little bit. Since I have a square image and also I would keep a square canvas. So that's look good so far. So this is how you load image in p5.js. So now with that image, how do we pixelate it? For this, we actually need to use for loops to create a grid, which is actually what I talked about in the previous video. I'll provide a link if you want to look into more details, but we're going to do that together again. So let's try to draw a grid, and that's overlaying this image, and later we're going to use the color from the image to fill each tile of that grid with the corresponding colors. That's how we're going to pixelate. And before we draw the grid, there are a couple of information we want to have. A couple of I'll put it at the beginning because these are the numbers that I want to specify. So one thing we want to know is the number of columns. I'm going to start with easy number 10, and rows again 10. And then based on those two numbers, what we can do after the setup, or let's actually put in draw, because we are going to be using those numbers in draw, is to calculate the width and height of the tile. The tile, in this case, it's going to be, when I say tile, it's referring to the pixelation, the large pixel that we're going to draw. You'll see once we start to get to that step. So tile width, how big we want the pixels to be, that is going to be width divided by the number of columns we have. And similarly, tile height is going to be height divided by the number of rows that we want to have. Again, I'm just going to run the code. I'm not expecting anything new, but I just want to make sure that there's no errors. And then once we have this information, we have enough information to draw a grid. So I'm going to start with a for loop, let column. I can start with column or row. This really doesn't matter. I'm going to start with column first. So column index, that's 0. And then column is smaller than the number of columns. And then column plus plus. So, and then I'm going to create another for loop inside. That is going to be row, and rows number r plus plus. Okay. Based on these two numbers, what we can get is the x and y position based on the column number, based on the c and r, which represent the indexed for the column and index for the row, and it starts from 0, goes all the way to a number depending on how many columns you have. So let's try to calculate that number. So x, that is going to be c divided by columns number times the width of the canvas. Y is going to be r divided by rows number times height. Now we have the width, the x and y. Let's try to draw the rectangle. X, y, column width, column height. Okay, I have an error. Oh, right. So sometimes I like to call it column width versus row height. In this case, I'm calling it tile width and tile height. So there you go. We have a grid, and let's actually call no fill so that we can see the image underneath. So we have a grid. Perfect. It's one step closer to turning them into pixels, into like pixelation. So now the only thing we really need here is to get the color of for each, pick a color for each rectangle or each pixels or each tile that we want to draw. And this number, ideally you should probably get an average of that square, but in my experience, if you use something like the center or top left, maybe ideally the center, if you use a pixel from the center, that is going to work perfectly fine for the pixelation for our purposes. So that's what we're going to do. And before that, before we get to the center part, we can just use X and Y, because X and Y right now is referring to the top left corner of the rectangle. So we can actually use X and Y. So X and Y, we can use that as the position of the pixel that we're trying to get the color from. So essentially, for each tile, we're going to use the very top left corner, use the color for that pixel. You can see how on the top, if you keep choosing top left, there's probably going to be some kind of a shift when you create a pixelation, but we can fix that over later. So we already have this. We already have X and Y. How do we get the pixelate how do we get that color? In order to do that, we need to do a couple of things, and that is to call a function called load pixels. So what this function does is to load all the pixels. Oh, I just realized I forgot to create a new sketch. Right. So what I'm going to do is I'm going to duplicate this. I'm going to duplicate this sketch. I'll probably later create another one for grid just so that you can see the different steps. And this right now I'm going to call it we can call it pixelation. Let's call it pixelation. I might change my idea later. So this is what we have. And what we're going to do is to call that function called load pixels. As soon as you call that function, what is going to happen is all the pixels on the entire canvas is going to be loaded into an array. An array is essentially a list of numbers or data. In our case, it's going to be the value for pixels, but we're going to talk about exactly how it's formatted. And let's actually talk about it right now. I'm going to switch to my camera, and I'm going to use my whiteboard right here. I hope it's in focus. So what we are going to do here, let's talk about how the pixels are arranged. So imagine we have a image that is only 3 pixels. 3 pixels by 3 pixels. Imagine this is the size of our image. How is it organized? In fact, each pixel is, let's create a bigger version of the pixel. Yeah, I'm not liking this. Where's my eraser? Yeah, it's probably okay. You can probably see it now. Let's draw a big version of this pixel. It's easier to see. Yeah. So how is it organized? Inside of each pixel, it's actually represented with 4 numbers. So I'm going to divide this pixel roughly equal size. And what are the numbers? It's going to be the R value, G value, B value, and the last one is the alpha, which refers to the opacity. 1 being completely opaque, 0 being completely transparent. So that's a number. And in this case, the opacity is actually represented in a number from 0 to 255. So 0 being completely transparent, 255 being opaque. Because we have the image I know there's no transparency, So this value is always going to be 255. So this is the same for all pixels. So there are 4 numbers for the first pixel, 4 numbers for the second pixel, 4 numbers for the third pixel, and that is also how it's ordered. It's from left to right and then top to bottom. So now there are a few numbers we need to note. Let me use another marker. Let's first note the pixel index. So let's number the pixels. So this is 0 pixel, 1 pixel, 2, 3, 4, 5, 6, 7, 8. And that's 9 in total. But in fact, because each pixel are 4 numbers, the total number is going to be a little different. So, and inside of this, as I mentioned, when you call the load pixels function, what happens is all the pixels is in one single continuous array, one single strip of array, and that number is organized like so. So RGBA, 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 and RGBA. Yeah. And then what we really need to know is not the pixel index. What we really want to know is the index for each color value. And how do we get that? Let's think about this. We start with 0, 1, 2, 3. So for within each pixel, we have 4 numbers. And then for this one, what's going to happen is 4, 5, 6, 7. And then 8, 9, 10, 11, and so on and so forth. So really, if whenever you want to get the R value for that particular pixel, the equation that you need is the pixel index. So pixel, let's call it pixel index times 4. And why? Let's test out. If you don't trust me, let's test this out. So for the R value for the first pixel, 0 times 4. That's 0. And for the R value for this pixel, that's going to be 1 times 4 equals to 4. And for this one, that's going to be 2 times 4 equals 8. Remember, this is 8. That's RGBA. RGBA. Like so. I think that's a little bit hard to see. I'm going to tilt that a little bit. So that's what's happening there. And I hope you can see it. I noticed that it might be a little small. I hope you can see it in the final video. And then let's test this again. The R value for this one is going to be 3 times 4, so 12. This is 11 right now, so next one is going to be 12. So what that means is whenever you want to get the red value, let's call it maybe something like R value. That is always going to be that is essentially going to be this, right? So now what about the G value? We want to get the G value. Well, let me step back a little bit. This is not a value. This is actually the index. Indexed. Okay. Let's call it index. So the R indexed. And then G indexed. RGB indexed. And A indexed. So the first one is going to be pixel index times 4. Second one is going to be pixel index times 4 plus 1. This one is going to be plus 2. This is going to be plus 3. And that's how you get that. And again, let's just try one of them. Let's say this is the second pixel, so meaning the pixel index is 2. And let's try to get the B value. B, not the value. Let's get that indexed. And that is 2 times 4, and then B value plus 2. That's where we get 10. And that's exactly the index, the overall array index for that value. And with that in mind, let's try to implement that in our code. So back to our code, we've called the load pixels function, and all the pixels is going to be stored inside a variable called pixels. But let's try to calculate this number first. So the number we just had right there. And in order to do that, so the x, so we already know the x and y. How do we get the pixel indexed? That index that we just talked about. And let's get back to the camera again. So the information we have actually is x and y instead of the pixel index. So we first have to figure out how to even get the pixel index. So let's again number this. So this is x, this is y. So this remember, these are the pixels. Right now we are not even talking about the tiles in our pixelation. We are talking about the actual single pixels. So this is pixel 0, this is x0, this is x1, x2, like on the vertical line, horizontally, this is 0, this is 1, this is 2. So based on x and let me remove this. Yeah, based on x and y, how do you get the index number? So let's pick this one. Yeah, how do we get that number 4 just based on x? So what's coordinate? The coordinate is 1, 1. What happens is, in order to count this, first you need to count all the, because it starts with rows, so first we need to count all the rows. So because each row is 3 pixels, so what we need to do is use the y coordinate times 1, 2, 3, and that's the width. That's the width of our canvas. We are imagining we have only 3 pixels in our canvas. So that we just count all the pixels that comes before the total number of pixels that comes before the pixel we are interested in. And then we need to count how many pixels we have gone so far from the left to right. And that is essentially to plus x. And the reason it was because all the numbers start with 0. What happened here is that when you add this number plus 0, you get 3. So 1 times 3, which is the width, plus 0, you get the 3, plus 1, you get the 4. So that really is depending on where you are at currently on this row, or on this on this row of pixels. So all this is to say the pixel indexed actually equals to this thing. And let's apply that to our code. Yeah. Get back here, and let's try to calculate the pixel indexed. So console and pixel indexed. That is going to be equal to, I'm going to refer to my note, y times width plus x. So that's the pixel indexed. And then how did you calculate the r pixel r index, y index? So let's actually write it out. Yeah, r index equals to pixel indexed times 4. Yeah, because there are 4 values in each pixel, so times 4, you get that. And then what's g indexed? That is going to be this plus 1. And I'm actually going to copy and paste to get the b and a, and that is plus 2 plus 3. So we just got all the RGB indexed. And once we have indexed, again, I'm just trying to show the whole process by listing out all this by creating multiple variables. So what's the R value? When you have indexed, remember all the pixels are stored inside of this this variable called pixels, and we can access that with square brackets. So R value equals to pixels, and then R indexed, and G value equals to pixels, and then G index, and B value equals to pixels, and B index. A value equals to pixels, and then A indexed. And there's actually still something missing, which we're going to talk about in a second. That is about the pixel density. But let's just try it out, and let's see what's going to happen. What we were going to do is right now, instead of no fill, I'm going to fill this color because I already know the R value, G value, B value, and A value. Let's fill that. And you might notice how it's not a complete picture. So why that? And that is because of something called pixel density. And the screen I'm using right now happens to have a pixel density of 2. And but we can change the pixel density to pixel density 1. As soon as I change that pixel density 1, voila, it's working. And we're also going to talk about more about the pixel density in a second. But for now, let's celebrate that this is working right now. And let me try to change different number of columns number and rows number. So let's see, maybe like 20. It doesn't even have to be the same number. 20. What happened? Yes. And then the rows number, 20. There we go. And then we can change this both to 40. Yeah, more pixels. We can even, if you don't want to see the stroke, since we never changed the stroke, we can put no stroke inside of a setup. And there we go. We have a pixelated image. And you might notice that there are some issues. Yeah, one of them is regarding the pixel density, and there's also some kind of random color here. And that, actually, I'm not entirely sure why that happened. But yeah, that actually never happened to me before. Interesting. X, yeah, but for the most part, it looks correct. That's interesting. So just to make the code looks more organized, I'm going to also add a +0 over there. And I'm sure as we work on more, as we get to the next step about pixel density and some other stuff, that problem probably will be solve itself. So let's celebrate our success by duplicating. Well, maybe I'll give it a name first. Pixelation with pixel density 1. And duplicate. And let's see how we can change that to pixel density 2, or I've only really used screen with pixel density 2. Maybe there are also screen out there that has different number of different pixel density, but we are going to, I think there's a typo, pixel density with, let's call it, with various pixel density. So imagine maybe there are pixel density 3 or 4 other ones. We will write code so that it will automatically adapt to that. So let's try to work on the pixel density, and then we will get to, yeah, we'll get there slowly. So let's talk about pixel densities. Let me switch to the camera. And what is pixel density? Pixel density really happened because now we have super high resolution displays, and what used to be one pixel now is multiple pixels. In the case of the monitor that I'm using right now, it has a pixel density of 2, and what that means is for each pixel, it's actually divided into 4 different pixels. So all this pixel that we talk about, it actually, and why is that 2? That's referring to both the width, 1 pixel becomes 2 pixels, both in terms of the height, 1 pixel becomes 2 pixels, and in terms of width, 1 pixel becomes 2 pixels. And when you multiply that, you get 4 pixels for each pixel. Yeah. So now with that knowledge, how does that change our calculation? Let's see. I'm trying to decide which marker I'm going to use. So with this information, really, it might sound more complicated, but really really what we need to do is just to multiply it by the pixel density for both x, y, and width and height. We might, yeah, not even need to use height. So all that is going to change. All the equations are still the same, except now y. When we have the y, when we get the x and y in P5, that is actually referring to pixel density 1. So even when you pixel density is 2, when you talk about x and y, we are imagining we only have 1 pixel here. And that's kind of what's getting more complicated. So in order to get the real pixel, real x and real y underneath, we simply multiply this by 2, multiply y by 2, or whatever number of pixel density that is, and then multiply x by 2, and then also multiply width by 2. Yeah. So we just multiply everything by 2, and we don't need to change anything else. Yeah, because now when we width is 3, it's actually now becomes 6. That's why width times 2. When we talk about the y position, let's say when we talk about 1, it's actually 2. So 0, 1, 2. Just everything is shifted by multiplying 2. And in terms of y and x, so everything multiplied 2. So let's try to do that, and then we can change the pixel density to 2. So in our code, first thing I'm going to do is I'm going to change pixel density, remove the pixel density. So instead of manually setting it to 2, what we can do is I'm going to first get the pixel density. So I'm going to use acronym PD and pixel density. So in fact, with this pixel density function, if you don't provide a number, this pixel density will return or provide the actual pixel density to you, and then we can use that variable. We can use this value to calculate. So now, with that PD in mind, what we can do is we can now calculate the width and height. So real width now is actually width times PD, and real height is actually height divided by PD. And then the rest, we don't really need to change that. So when it really matters is in terms of the calculation of the pixel indexed. So y, we can also, let's create another variable. So the real x is x times pixel density, and real y is y times pixel density. So now really what we need to change is, yeah, the width and height needs to stay the same elsewhere, because we are kind of imagining that these width and height. But for the pixel density, when you actually start counting this, you get the real all the pixels. So what we do is, instead of y, we need to use real y. Instead of width, we use real width. Instead of x, we're going to use real x. And now if we run the code, voila, everything works perfectly. And this time it's high pixel density. And when you change the pixel density, if you change the pixel density to 1, what you will notice is the image will appear a little bit more slightly blurred. And that is because now you are using the physical pixel to represent one pixel. That's why it's not as crisp. So this is the reason why I want to introduce this, because I prefer having, I think it's really nice to see the actual sharp image, the sharp canvas. So you'll notice we still have that issue of, even though we incorporated the pixel density, we still have the issue of some of the pixels being a little bit weird. So now let's start. This is actually a perfect example for me to demonstrate like one of the issue, and I suspect that's where that problem come from. Is right now we had when we are doing choosing the number of columns and number of rows, we're imagining that you can perfectly divide 400 by 40 and you get 10. So each pixel's width is going to be 10. But sometimes maybe we want like odd numbers. So let's say if this is 19 and you 19, and this is where things just completely messed up. And why did that happen? That happened because when we calculate the tile width and tile height, when we do all this calculation, we are assuming that we only have integers. And once you introduce this kind of irregularity, you don't get integers. When you don't get integers, and remember that the pixel index that we are calculating, it has to be an integer. And that because that is representing the indexed. And because it's indexed, it has to be an integer. When it's not integer is when it's a decimal number, let's say 10.1. Among all the pixels, the computer doesn't know which pixel does it choose. So the pixel index is really important for that to be a integer. Yeah. So when that happens, what we're going to do is let's try just simply round this number and let's see what happens. And there's still some issues, again, because the fractions are really happening at all over the place in this case. So there are some really important stuff that we need to, let me change this to back to 20, and let me actually duplicate this. And this time we're going to tackle with pixelation with uneven pixels. Or yeah, I could have, yeah, that name deserves a little more thinking, but I'm going to call it that for now. So 19, yeah, so that's problem. So what are the stuff that we need? We want integers. Essentially, we want the x and y to be the integer. And let's actually create yet another variable. So let's call it integer x, and that is going to be, let's round it up, round real x, and integer y, that is going to be round real y. And really, that's real width, that should be all we need. And real y, let's change that to integer y. Real x, let's change that to integer x. Let's see. And there we go. And notice how now it's finally beautifully, all the pixels are, the image is beautifully pixeled, and we do not see any of those irregularities. And I suspect previously the reason why it happened was because sometimes the pixel index is not integer, and that's causing some problems. And now let's play with these numbers. Change to 29. Now I'm intentionally choosing weird numbers. 31, yeah, 49, 59, and all very beautifully pixelated. 40. So great with uneven pixels. So that's a great step. And we can call it a day. It's actually being a pretty long video, but I just want to do a couple more things to make it, to add more excitement to this. And so now, first of all, now you have this this sketch. We have 46 line of code of the sketch, but you can pixelate any image, and that also doesn't have to be square. Let's say if you want a different shape, and everything just automatically adapt to whatever value that you enter, and it also the width and height doesn't have to be regular. You can change all that, and that will all work perfectly. So that's great. And let's duplicate this, and let's try a couple more fun stuff. Pixelation, I'm going to call this. One thing we can try is circular. What if we don't want rectangle pixels? What if we want circular pixels? And in order to do that, we actually, well, also conveniently, we're going to solve another problem. Remember that right now the color we are picking is the top left corner of each rectangle. And if that idea of using the top left corner of the rectangle or the tile is kind of, yeah, make you stay keep you awake at night, maybe what we can do is right now let's try to change our code so we actually use the center. I actually didn't try it beforehand. I hope everything goes well. So first of all, yeah, let's switch. Let's make it even more pixelated so it's easier to see everything. So this actually demonstrates where the problem comes from. When it becomes a problem, the more pixelated it is, the more off center it becomes because we're using the top left corner. That's why the whole circle, the whole sphere actually goes a little bit to the bottom right. And that is exactly the reason why we want to fix this problem, because that will keep some of us awake at night. So what we are going to do is to try to get the center. So when we calculate the x, instead of this x that we have here, we want the center of that rectangle. And how do we get that? In order to get that, we simply need to add half of the width and half of the height of that tile. So tile width divided by 2 for the x, and then tile height divided by 2. And because we did the rounding later, that's the only thing we need to change. And of course, there's a new problem. It might not be super clear, like why is this happening? Why did that happen? That is because when we draw rectangles, by default, we are, the x and y refers to the top left corner of the rectangles, which worked perfectly fine because the x and y was the top left corner. Right now we want that to be the center. And we actually have the option of changing the mode, the drawing mode for a rectangle. We're going to call it rectangle center. So right now, when we are drawing a rectangle, we're specifying the center of the rectangle instead of the top left corner of the rectangle. And you see how right now the sphere, as pixelated as it is, it feels more centered. And let's bring it, let's give it a little more resolution. Beautiful, very much centered, just like the original image. And let's now change the name. So pixelation with center color. And now let's finally give it the fun. Pixelation maybe I'm going to put circular at the beginning. So circular pixelation. So at this point, maybe you are bored with rectangles, or maybe you like rounded corners. Well, let's try to do that. So it's actually pretty simple. We already get rectangles. The only thing we need to change is I just comment that out. So it temporarily disable that line of code and change that to circle. And because we have both width and height, I'm actually going to use ellipse. So we can utilize both the width and height. So that is going to be x, y, tile width, and tile height. And there we go. That's circles. But of course, we actually see the original image underneath. Maybe that's a look you were going for. That's perfectly fine. But what if we only want to see the pixels? If that's the case, what we can do is this background is actually not doing anything because this background happens before the image. The image will cover that background. What we can do is we can draw a background that cover the image before we draw the pixels. But where we put that background is actually really important. We don't want to put that background before load pixels. Remember, load pixels will load all the pixels on the canvas. If you put background before load pixels, what that means, all the pixels you load are the gray color, are the gray pixels. So we want to make sure we put this after load pixels. So as soon as we finish loading the pixels, now you can draw whatever background that you want. So usually I would choose, it's really up to you. I would choose either use the white for background, or I'm going to use black for background. In this case, I think I have a really bright color, bright pixels. I like seeing it with a dark background. So that's what I'm going to do. So now we have circular background, circular pixels. How exciting. And let's duplicate this again. And similarly, wait, it didn't duplicate. Let me try this again, duplicate. Similarly, we can also create, oops, I accidentally delete that. So rectangular pixelation with rounded corners. Yeah. So what we can do is, so for rectangle, now let's switch back to rectangle. For rectangles, there are actually, for rectangles, we can actually specify more than 4 parameters. And the next parameter is going to be the radius for the corner of the rectangle. And let's try a number like 3. Now that's so right now the corner radius for your rectangle is 3 pixels, and then we can change that to like 10. Yeah, so it's become more and more like a circle. And you can also use in terms of percentage. So maybe I want it to be the 20% of my tile width. Maybe that's a little bit too little. Maybe 40% or 30%. Really, now you can get rounded corners. Yeah. So that's one thing. And what's even more exciting is we can even animate them, and that's where it really gets exciting. So let's try to do that. Now let's try to animate these circles. Maybe this video is really gonna be super long. I'm really not I wasn't planning to make long videos. I want the video to be short, but I guess I said it. We were gonna animate it. Let's try to just add some simple animation, and that animation can actually be the corner radius. So let's try to animate the corner radius. In order to animate, I'm going to add a sine function. I think because this video is already so long, I'm probably only gonna explain how exactly it works in a different video. For now, I'm only going to demonstrate just to show you what are the possibilities of this pixelation. And I'm going to add create a new variable that's called corner radius, and I'm going to use calculate the corner radius based on the width of the tile. And what I'm also going to do is to add a sine function in order to calculate the size of that corner. And what I'm going to do is add frame count. So frame count is a variable that automatically updates depending on the number of frames that has passed. It will always show the current frame count, current number of frames that have passed. So if I use this, it's probably gonna be pretty crazy. Oh, actually, it wasn't as crazy. Oh, I haven't used this number yet. So if I change this, replace that with corner radius, it's probably gonna move super fast. And in fact, it actually gave me an error. Failed to execute. Maybe this number changed like too drastically. So what I really need, what I want to do is make this a little bit slower. Yeah. Right now, I think the issue is that this tile width is at some point is going to be get to a negative number, and that will probably cause a problem. So let's fix that by mapping this value, the output of the sine function, from -1, +1, or -1 to +1 to maybe 0, and then tile width. Yeah, so now that's animated. And 0 to tile width. So this is where you can add a little bit of animation. And what's even more fun, let me add animated. Yeah. I'm going to share the links to all the sketches down in the description. So what I'm going to do is I can also use R. And yeah, this is really getting too complicated than I want this video to be, but let's do it. So what we can do beyond this is that we can add R and G inside of this input of sine. So what I'm going to do is first, yeah, it really doesn't need to be that complicated, but I like creating more variables to help code be more readable. So what I'm going to do is to create first the x normalized x is going, so normalized meaning converting the x from 0 to the width to 0 to 1. So normalize, so let's try to normalize the x. So x is going to be a number that's originally from 0 to the width. But I want to convert that number into a number that's 0 to 1. Normalize x. And copy this. I want to get the normalized y. And then height. So normalized y. And then what we do is we can then add pi depending on, yeah, I'm normalizing it because that make it easier to get a perfect cycle of sine wave. And normalized x times 2 pi. And you'll see how the x change based on so right now, depending on your x coordinate, the corner radius is different. And now I can add this normalized y, the same thing, times 2 pi. Yeah. Actually, normalized y. Yeah, I realized there's nothing happening on the y, so actually there's a typo. So now it's diagonal. And what what other thing you can do is, depending on, let me do a edit tidy code to make things a little more readable. And this kind of keep things a little more organized. So this is changing diagonally, and if I add more, let's actually create more variables. Why not? So frequency. This will be referring to the frequency. How many complete sine wave you want to get on x and y. So frequency. Let's start with 1. Frequency y. And that frequency needs to be multiplied here. Yeah. And 1 because right now nothing changed. So as I change this number, you will get to see different amount of frequency. So let's start with 2. So now you see more waves. 3, 4, or 5, and yeah, earlier I did 10. Maybe let's stop here. I think this we're already getting like a lot. We're doing a lot more than I was planning to do. And of course, you can always go back and change the number of pixels that you have here. And I think to my taste, it's a little bit, the frequency is actually too high. Maybe I'm going to change it to 0.2. Oh, that's an interesting effect. Maybe something like 5. That's a little bit too fast. If you want to change the speed, it's really this number here. Yeah. I think there are definitely different ways to experiment with this. I'm going to again change this to a smaller number. I think that looks more interesting. And let's try to compare this and the original image. Let me put the original image at the bottom. This is just to compare. This is the original. This is pixelated. Again, this is the original. And this is pixelated. Great. And so hopefully you had as much fun as I did. I kind of really went off a tangent to start animating, and I really think at this point I should stop. And but I hope this is I hope you had fun. I hope you will find Pixelation something useful that you can use in your own work. Feel free to experiment. And if you like the video, please like the video, subscribe, and also if you have any, if you make anything out of this, if you create any pixelated artwork, pixelated project, please share it with me in the comments, and I would really love to see them. And and thank you for watching the video, and I'll see you next time. Bye.